All right, so it's a little hard to read on here, but you have them in front of you, so hopefully that'll kind of suffice. I'm going to write on the sides, though. These are AP questions. With the shorter reviews, I'm going to be more of the person kind of working through them and going over them. The longer ones that are set for like 2 to 2 hours and 15 minutes, that's where we kind of come in and out, and you're going to be responsible for coming up with them. The kind of goal between all the review sessions is we cover at least everything twice. So I'm doing big topics, and we're kind of reviewing them. So as you can see in the top, we're doing acid-base equilibrium today, free energy thermodynamics, electrochem, and then a little bit about chemical equations. And hopefully all that will just help reinforce and move us in the right direction, okay? I'll show you how things are graded as well, and hopefully we're in a good place when we're all done today, okay? So here we go. This one's from 2011. It says, now please understand, if you ever do see a problem that says choose 2 of the next 4 problems or something like that, those are older tests. They've had so many different kinds of formats. Please understand that the format's different than the questions themselves. So just be mindful. That's not what it says on this one, but sometimes it does say that. All right, so you have 3 beakers above, beaker 1, beaker 2, beaker 3. It says each of 3 beakers contain 25 mils of a 0.1 molar solution of HCl, NH3, or NH4Cl as shown above. Each solution is at 25 degrees. A, determine the pH of the solution in beaker 1. So, to someone, what are you going to do in general? What's the idea? Negative log of H plus. Now, why can I do that for beaker 1, just negative log? It's a strong acid. So, here we go. So, pH is going to equal negative log of H plus, right? And that's how we're going to be starting for that one. Please don't make mistakes on numbers. Please don't get rid of values as you go. Right, so that's going to just be 1.00. And that one, there's not much more to that one. That one would have just been 1 point. Done. Okay, so I like these kinds of problems where they set something up on top and you kind of keep going back, because what is happening is you're having to kind of pick. They usually don't make it overly complicated, but there's little intricacies of each. Although that could be bad and a really uncomfortable feeling if you don't understand it, but if you do, you're probably going to really sink into a lot of the problems because of that. In beaker 2, the reaction, it gives it to you, NH3 plus H2O gives you NH4 plus OH minus. I hope you can read this too. I think it came out clear enough. I actually printed them out earlier and they were all pixelated, so I reprinted them, but can you read it okay? I don't think my father would be able to read these, but you guys have younger eyes. The value of Kb for NH3 is that I. Write the Kb expression for the following. Just the Kb expression. So, give you a second to do this. What would be the Kb expression? This is important because these are the things that people forget. These are the things that should be the quote-unquote easy points that kind of compensate for the ones that we stumble on, trip on, lose sight of what we're supposed to be doing. So what is the expression? Again, you really can't read it off the front board, but you definitely have it there. Hint, if you're stuck, you shouldn't be really writing any kind of real numbers except the ones associated with the formula. Done that should be it. Just a point. Again, if you look at this goal, it's just 1 point. 1 point is huge. Every point we can get is a big deal. So do the best you can. And as I've been saying, don't bail out. If you get stuck on something, assume that the next problem has nothing to do with it or you have a chance to justify it. Worst case scenario, we don't talk about this much. If you ever need a number and you knew you needed one, just say assume, I'm going to make this up, assume the concentration of whatever you're dealing with is, and make up a number, 0.01. And then you go forward. Like, you can still do calculations. You should never go, oh, I know that. I know how to do all that if I just knew that previous number. say that that's what, just make up a number and then show that you know the work.
Since it gives you the KV, you have to put the 1.8 times 10 to the
It's good. You mean like here instead?
Yeah.
That's a good question. Because it says the expression, you would not probably get it wrong if you put 1.8 times 10 negative fifth, but an expression usually doesn't deal with any concrete values. I cannot imagine that they'd mark that wrong on you though. If you're really, bro, let's say you get to the test and you're like, I don't know if I should, like you kind of hesitating, what I would do then is do an equals on the other side and then write it there. They're never going to be like, no, you moron. No, they're not going to say it. Okay. Double I, calculate the OH. All right, so there's more work or there's less work with this? Anybody, like, what's the shortcut to this? OH minus. I have to do calculations. It links with this. I don't get this. Anybody else? Erica, do you know the shortcut to this? Instead of, I'll give you a hint. The long cut is the long cut. The full on is like an ice box. No, that would be PKB. It's not a bad idea. Exact, right. And the reason why, and you're like, whoa, wait, I didn't hear that. It's x squared over initial minus x. Why? If you look at the equation, and it's hard to see this here, but you'd have 0 and 0. So at the ending of this, these would be x's on that equation. So you could totally set this up because you're given an amount. Well, what's the amount? 0.1 molar of NH3. So if only you have an amount of a weak base, what you could do is simply this. And I hope that makes sense. You could do an ice box. You definitely could. I think half of you would start doing, if you're not sure and you're in an equilibrium problem, you're like, I don't know how to set this up. Immediately go, okay, ice box, I'm just going to set this up. Well, 0.1 would go underneath your NH3. This would be 0 and 0, plus x, minus x. Oh, wait a minute. That's x squared over initial minus x. Like, hopefully, most of you, that would trigger that at that point. So then x will equal concentration of OH minus, which equals, I have it right here, 1.34. Due to time, I will be your calculator more today than some other problems. But is it always, if you can go ahead of me, that's a bonus.
Would you want it to say scientific position?
You could do either one. You could do either one. Just on a side note, did tennis players at all tell Mr. Sridudo that you're going to be late, or are you guys leaving early?
Oh, we're leaving early.
Okay. I don't want him to have a heart attack. So, okay. Thank you. Also, I could see him like, where's some of our guys?
What time do we need to be there for him to like come over there?
Quarter 2 probably.
Okay.
Well, but he doesn't know.
No, I don't. I assume like you know.
But I already told him I wasn't going to be there.
So just
We'll get a hold of him. All right.
we're leaving earlier than that, so.
All right. 3:30 would be awesome. Okay, letter C. So, by the way, 1 point is earned for the correct setup. 1 point is earned for the right answer. That's 3:35. In beaker 3, reaction. They give you a different reaction. NH4 plus water gives you that. Calculate the Ka. How do I do that? How do I get the Ka? Any thoughts? Jeffrey? Okay, so, and if I don't say the numbers, you're right. It's that. You're right. What you said is right. But remember, how can you do that? Because if you look at that equation, NH4 plus is the conjugate what of NH3? Conjugate acid of NH3. If you have a conjugate acid-base pair, you can do Kas and Kbs. Okay? And that's all you gotta write. I think that's honestly, this is the perfect way to do it, I think. I mean, then you're showing what you do, and then you put it in there. Minimum, at least put the numbers in. And you got to show your work. You get a point earned for the correct answer. Okay. Double I. Okay, the contents of beaker 2 are poured into beaker 3. So we're going to amp this up a little bit now. And the resulting solution is stirred. Assume this volumes are additive. Okay, so they add up together. Calculate the pH of the resulting solution. Okay, so this is what I like to do personally, is I like to think about what's actually occurring, what's present. So there's two different things that are present. Oops. There are some other ways to do this. Like I'm just looking at the answer key right now. They did it very differently than I did. Very differently. But, and actually it doesn't have to be either way. This is what I did. I want to just kind of talk about what happens. What if I just assume, okay, they're both in a solution? It could have been either solution I picked, because it's beakers 2 and 3. They give you both equations. Don't both equations have what's present from there? And the answer is yes, they have them both. Oops. Wait a minute. What's that? And I can't do that, that's illegal. I gotta do the H3 plus as I'm walking away from it. Okay, you could have picked the, why'd you pick that one? Why didn't you pick the NH3 one? I could have picked either one. I'm mixing them together. So if you're in doubt, like I don't know what's happening right now, well, a reaction probably occurred. You're mixing beakers. So that's my first step. That's mentally what I think about. Hey, I'm mixing two things, a reaction's occurring. So then there must be a reaction, a chemical reaction. So if you look, what you have is you have 0.1 molar of NH4, and you have 0.1 molar of NH3. I'll show you how they did this in a second. But basically what they're saying is that you have equal amounts of each. Okay? You have equal amounts of each. So, what could I do? There's a couple ways actually. Brody, what?
Why don't you cross out the HOH because that's water.
Okay.
And then that would give you 0 for the H3 plus.
I like it.
And then it'd be positive X for NH3 and H3 plus.
Okay.
Negative X.
And then I just go forward and I plug it into an expression. I like it. I like that you're going to do more work than you need. Juliana? You're right. Nothing you said was wrong. Perfect. I can do Henderson-Hasselbalch because they're the same. And honestly, because it's under the same, you're going to have the same amounts, the volume actually isn't going to be a huge issue. But you're exactly right, Henderson-Hasselbalch. What if I, so that's, I wanted to show it that way. You can put this in Henderson-Hasselbalch. The other concept, because you notice this, what's actually occurring here? Like what's the final answer, like, reflecting? Well, this neutralizes, but this is going to be made. So what Brody wrote here does tell me that I'm adding this. So I'm going to gain H plus, and these are gone. So just for a second, if this is an acid right now, if this is what the answer. This is, I didn't do it this way, but the answer key does it like this. We talked about this in our lab. Oops, yeah. These equal each other, right? So those cross out. What is this called? This is the pKa. This is the pKa. Okay? So, we just found it out. I'll tell you now, they purposely set this up beforehand to try to get you to utilize the, excuse me, the Ka. So I can just take negative log of that and I'm done. Okay? I can just take negative log of the 5.6 times, I'm looking at points. 1 point is earned for noting that the solution is a buffer. So either you could have crossed them out here, or the fact that you use Henderson-Hasselbalch equation, you get a point for that. I did the Henderson-Hasselbalch. I'm going to write that out once. I did this. did that. But honestly, it's just pKa. And you're done. And then 1 point is earned for the correct pH. It's 9.3. You could have predicted that it was going to be basic only because the Ka is much smaller than the Kb. So if the K is smaller, that means that the acid, it's not as strong of an acid. The base is stronger than the acid is. It's still both weak. That's the way that one works. We have 2 more and we're done with this one. Letter D. The contents of beaker 1 are poured into the solution made in part C double I. So now this gets a little confusing. The solution is stirred. Assume the volumes are additive. A little confused because I feel like that's not being taken into account. Talk about that later. Is the resulting solution an effective buffer? Justify your answer. Okay, so you are taking beaker 1. So this is beaker 1. Okay, I just want to visually write this out once. And you're putting it into the solution that we just had. Is this the same I want to get the same. Well, it doesn't really matter which way I write it. No, I started the other way. It's not a big deal. Either way, it makes. Sorry, water. Stop it. Is that going to be an effective buffer? So basically, what you're going to do is you have. I'm just thinking about this. This isn't actually what is going to occur yet. I'm adding acid. Okay, so what does the acid have to add? I just wanted this to be on the same screen. If I add acid, this is what I want to think about. What does it have to add to? Acids always add to the base. Which one's the base? NH3 or NH4 plus? NH3. I just want to visually show this to you, and then we can talk about this. This is what we've been learning in this chapter about, okay, how does this all work? Well, it's all about amounts and consumption. So you could just show a little bit about this. This had 0.1 molar. This had 0.1 molar. And this had 0.1 molar. Regardless of volumes, they don't need to have a number. So yes, technically, I'm a little thrown off because it says additive, and then we didn't really utilize that in double I. But this one, you could have put this over a total of 0.75 milliliters, and then you got millimoles. But in essence, who gets consumed here? Like how much? Which one? What happened? It's basically going to consume all of it, right? And if anything, if this was diluted over 50, this is even less. So what's basically going to happen is all this is going to be driven over to the side. So what I'm trying to say, is this an effective buffer? Better question. What needs to be present to be an effective buffer? There's 2 things. And we're going to figure this out today. There's 2 things to be a buffer, a good buffer. There's 2 main things that you need to know. What's an effective buffer? One of them is easier than the other to think about. What do I need? Trevor?
Resist pH change.
That's what it is, yes. How do I get an effective? No, you're right.
Excuse me, Jen Heck, if you're in the building, could you please call Rebecca Buds at 6737? Thank you.
My best 2 years ago we're doing these reviews, and they played, I have no idea why, through the loudspeaker, Shakira for an hour and a half after school, like loudly. No reason. Just like 2 CDs worth. And I was recording it. It's like, we couldn't hear you speak. It was what was that? Was that Shakira? I'm like, yes, it was. So, all right, what needs to be present in my equation? Is that a hand you have?
Substantial amounts of acid.
So I need, how do I write? I need acid. I always hate to write it because I don't want to commit to acid or base. I need conjugate acid, conjugate base amount, pairs, right? And then I need them to be large and equal. Like So first, maybe this, present. Let's do that. You need the conjugate, you need conjugate partners present. It's not a good way to write this. There's no real easy, I can write A, C, B, or B, C, A. I mean, I need one or the other, right? I need a conjugate pair. And then they should be large and equal. The larger they are, and the more equal they are, what they do is resist pH change. Why isn't this a good buffer? Besides that it was already small, I don't have this anymore, right? I don't have any of the base left, because the acid consumed it all. So is this going to be effective base? No, because the acid consumed all of the base. I don't have amounts on each side. I don't have a base and a conjugate pair. I'm going to read you exactly what it says. The resulting solution is not an effective buffer. Virtually all of the NH3 in the solution will react, leaving mostly NH4 in the solution. Since only one member of the NH4 plus NH3 conjugate acid-base pair is left, the solution cannot buffer both acid and base. You don't need to have specifics. You won't even need to know if it's all gone or not, because we didn't have to crunch the numbers here. You can kind of get a feel when they need numbers or not, because they'll ask for specifics. You can just say yes or no. If it's yes, most of the pair is still present. This is clearly going to more or less be consumed, if not all the way. Okay, so just remember, you got to have both, and they should be large and equal. So if it ever's asked which one is the better buffer, it's the one that has larger amounts, and they're more equal on each side. Okay, so that was only 1 point though. So again, after all that, you're like, I don't know, 1 point. You let it go and you move on. Yes, 1 point's important, but also it's also important to be in a good mindset where you also know it's only worth 1 point. And don't make it where it's like you're fighting, and then you don't think it's important, but then when you don't know it, you all of a sudden have created it into like a 4 or 5 point problem, and it's not. Like, keep it in context. Final, double I. Calculate the final NH4 in the resulting solution at 25 degrees. So, shoot, I just wrote that out and I should have left it there. So, this is what I did. So, sorry, if you just did write this one, you can just use it again. I'm going to use this one right here. Okay, so, this is how I did it. I did it the fastest way possible. And shoot, okay. It's 0.1. There's a couple things we have to know. First, these are going to be the same regardless of what it is, because it's going into a solution. So this is going to be subtracted. We got to figure out what that means. So I'm going to talk about that right now. First, just so you know where all this is coming from, I started with sorry, can't see it. 25 mils. Sorry. Just want to show you. There's other ways. They did this very differently. I don't think it helps anymore. So this is initial, like before it's mixed. Okay, so if that's 0.25 millimoles, all these would be, sorry, not 2.5 millimoles, all these would be 2.5 because they're all the same initially. You mix them all together, you're going to subtract it or add it. So in this case, okay. Molarity has nothing to do with, moles have nothing to do with volume, but then concentration has something to do with volume. So when all said and done, I have 5 millimoles, and this is where the only time that the volume matters. It said that the solution is additive. So what's my total volume? It was actually 75, not 50, because I'm adding each. If you thought 50, each brought 25 to the table. So, whoops, I need 75, and I can do milliliters here. And then you'll get a final concentration, and you guys can calculate that one. And to believe it or not, you get 2 points for that. One is if you just found the moles of your NH4. So even if you got confused with concentrations and everything else, if you discovered the moles, you would be fine. And this is the longest of the problems. This is why it's taking a little longer. And I got like 0.06 something. You did that right. Okay. And then the second point's the actual molarity. All right, once you're done with that, we're going to jump into our thermochemistry free energy one. I got 0.0667. All right. Okay, here we go. Next one. Jump into this quickly here. I think I have the same problem. I do not. What is going on? Okay, different problem. Good. Here we go. Answer the following questions about glucose, C6H12O6, an important biochemical energy source. Sorry, I cannot tell you what these are worth. I do not know. I have a different one printed out. Write the empirical formula of glucose. What's the empirical formula? Simplest whole number ratio. So I hope this makes sense. I'm assuming 1 point. I would be shocked. If anything else. All right. Then it says, in many organisms, glucose is oxidized in carbon dioxide and water, is represented by the following equation. And then you get this equation. A 2.50 gram sample of glucose in excess of O2 were placed in a calorimeter. After the reaction was initiated and proceeded to completion, the total heat released by the reaction was calculated to be 39.0 kilojoules. B, calculate the value of change in H. We always have a hard time with this stuff. In kilojoules per mole for the combustion of glucose. Okay, this is how this works. They already said that this is the amount of energy released. It's asking for now. This is the key thing for you. They just said kilojoules here. This is kilojoules per mole. So all I got to do, this is how much actually was released from 2.5. They want to know now per mole. There's the big clue. I get to a problem if I don't know this. Check the difference in unit. All I got to do is now get this into kilojoules per mole. That's the whole point. So I was given grams. Here we go. This is how I would do this. And it's the glucose. I'm going to run out of room, so I'm going to have to break this down a little bit. 1 mole of that, if you add that all up, 6 times 12 plus 12 plus 6 times 16, I believe that's 180. It's kind of the standard. There's one more T-chart here, like step. Now I'm in moles. I can do kilojoules per mole. So, if I want to really make this right, if you're writing, please see. It said it was released. I'd actually find the word released. That's what that means. So I just calculate it. That's a hard problem. I don't think that's an easy thing to recognize. We haven't done it for a while. You're just kind of converting. But that is how that works. So how did I recognize that? Per mole. Wait, they gave me kilojoules. Now it's also in kilojoules per mole. What the heck? Make up your mind. It's not a mistake. So now my answer is negative 2810 kilojoules per mole. Because usually whenever they give you a value like this, it's generic for a reaction. This one they literally said that much produced that much. Did I do the wrong math? Is that joules? Is it 2.8? Did I just, can you? I do not have it. I do not have 1 mole. What?
You're supposed to do 39 divided by the total amount of moles from the gram sample. So like the moles was 0.014, and then do 39 divided by that.
Wait, what are you saying? What is this?
Like that answer is 0.01.
39?
Yeah, 39.
Yeah. Okay. That's actually what I have written down. I don't know why I wrote it down like that. 0.0139. Thanks. That's what I have in my work. Okay. Yeah. Okay. The reason why, if that right now, if I did 1, don't write the green. If I did per 1 mole here, that is then, you're just saying per 1 mole. That's just a normal enthalpy. So what this did, which I had the right work here, but then I combined it. If you did the answer to this per how many moles you have, that would be per mole.
Where did you get the 0.0139 from?
That equals, this equals that. So you figure out the moles. I bought, it's not a continuation. I'm looking, I printed off the wrong thing, so then I'm going off of like some hen scratching that I had, and I ran out of room. I thought I just continued it, and that makes a lot more sense, obviously, now, seeing that. It's, you figure out the moles, that's how much you have total, so the amount you have over the moles that you have, that's how much you have per mole. Okay? So it should be more, by the way. It shouldn't be less, because you don't have a mole. You need 180 grams to equal 1 mole. So, yeah, right. So if you had 180 grams of this, that's how much you actually make per release. I am sorry, I don't want to make any confusion when I'm doing reviews. All right, letter C, if I can even read this. When oxygen is not available, glucose can be oxidized by fermentation. In that process, ethanol and carbon dioxide are produced, as represented by the following equation. So here's an equation. Again, here's something that we will need to use. The value of the equilibrium constant Kp for the reaction is 8.9 times 10 to the something. Is that 39? Yeah. Well, it's even harder to read on my sheet. All right, I. Now, some of this might be totally independent. I might need a value later, though. Usually when they make you do this, I'm not trying to look ahead. Usually when they make you find this, you're going to need it. Not always, but a lot of times you will. So I, calculate the value of the standard free energy change in G for the reaction at 298 Kelvin. Include units with your answer. All right, I don't know what to do. Oh, yeah, change in S and change in H. Okay, the minute I find change in G, I just go to my equation sheet, and I take a breath, and I say, what have they given me? What they've given me is a K. Okay? So this is the equation I need. Negative R. It is not about memorizing. It is about simply applying. I have everything I need right now. Okay? This is energy. So R has to be at 8.314. It's at 298. And I'm out of room. I apologize. And then my K.
So you can just use, like, if they give you the K, like, concentration concept?
It would have been the same thing.
Oh,
Yeah,
that's weird.
I know. And that's what you get. Just a couple more on this one. Double Y. Calculate the value of the standard entropy change for the reaction. Okay, so I'm like entropy. I'm not sure. Well, think about what you've done. This has kind of been reset. So what do you have? You just solve for G. Yeah.
Do you have to bring the G as kilojoules per mole, or can you just write it as kilojoules?
The reason why, oh, shoot, I thought it said that in there. You could have just written either one. If it doesn't, you gotta at least have the kilo. If you, I'm a little thrown off because I don't have my other sheet that I had with this one. Is that actually larger? Was it? This is right. Is it 228,000? Am I frustrating someone? I think. Yeah. So I just condensed it. This was in joules. It can be in joules or kilojoules. Anything that's over 10,000 usually we write as kilojoules, so not joules. So that is larger. I didn't want to make a mistake in it. That was supposed to be condensed. So that was in kilojoules. If you want to do 228,000, that's fine. All right, back on track. You got change in G. This is the one that people miss. You already have your change in H. So, I'm going to scroll down so we don't condense this one down. So, double I, let me actually just do space here. I have G, I have H, I want to find S. This should be this equation. And you just plug it in again. Major importance, you have to correlate your units. Now, this one is asking for a very specific unit. So either you can prep it before or you can prep it after. It doesn't really matter. I'm already in kilojoules both ways, so I'm going to keep it as is for now, and then I'll solve for it later. Or I could go the other way. You know what? I'm going to calculate. I guess you could convert it. You can do either one you really want. Let's do it right away. $298. I'm going to guess this is positive. The reason why? Reactions that are negative for G, this is a good review, are favored. It's also very much favored when you lose energy, and it's very much favored when entropy increases, disorder increases. So because these are both negative, it corresponds to a reaction that is spontaneous or favored. So I'm going to guess that change in H or S is then positive because of that. And I got something roughly to this number. And it's very important. You have no choice. If it asks for a unit, you better answer it in that unit. I had no choice there. Even if it's really large or really small, you don't have a choice. Just a couple more. Indicate whether the equilibrium constant for the fermentation reaction increases, decreases, or remains the same if the temperature is increased. Justify your answer. All right, this one I would guess most students don't get right. What are you looking at when you talk about temperature? When it says increase, decrease, when things are, it says equilibrium. So if it's about equilibrium, then it's about shifting. So when we talk about increasing temperature, it's about that. Where do I put the E? You're like, oh, that's what that is. Where is energy existing on here? As a reactant or as a product? It's a product. So what I'm thinking about is this. It's releasing. It's not gaining, it's releasing. So now, what's the question? If temperature increases. So if temperature increases, the reaction is going to shift to the left. And if it shifts to the left, just a reminder, K is products over reactants. So wait, K never changes. All constants change when temperature changes. All constants change when temperature changes. So if this increases the temperature, the energy, the reaction is going to drive that direction. Regardless, I'm not arguing that there's an arrow or not. It's going to cause it. It's saying there's an equilibrium constant. So it's going to drive it to the left. So my K will become, well, so we're going to use that word, right? Or decreases. K decreases because this is how I would say it. State the facts. K decreases because it's an exothermic reaction which would drive the reaction towards the reactants. Or you could talk math. It will cause the numerator to decrease and the denominator to increase. I mean, you could talk about that if you wanted to. But either way, it's going to drive it to the left, which will cause the K to be less. Well, yeah, but you said even if it drives, it'll level out. That's unless if temperature change. Temperature changes the K. Right, last one, and then we'll get to. It's going a little longer than I wanted to, but at the same time, I think it's all good. So I hope. D. Using your answer for part B and the information provided in part C, calculate the value of change in H for the following reaction. So they give you a new reaction. What triggers your, what's a trigger here? What do you think happens here? Any thoughts? Just looking through the problem. So it says B and C. Any thoughts? Kevin, what's your thought?
Well, do they add? Or like, are they combined somehow?
Yeah. So there's two different reactions, right? I mean, basically, to me, it's like that's a new reaction or a new chemical equation, but it looks like it's using molecules or compounds from other ones that I've seen, right? Well, that's one that was given. That's the other one that was given. So what do I have to do to all this? Well, looks like I got to multiply this by a half. And it looks like I need to actually cut this one in half too. If I do all that, this cancels out. This stays, which I want. This stays, which is what I want. That stays, and that stays. So more or less, I'm taking half of this change in H, and I'm taking half of that change of H. What I do is I just add them up. So it's negative 2810. But I have to flip. I flipped one though, didn't I? Sorry, I'm trying to rush this a little. Right. I'm trying to find where. Oh, right. It was the opposite way. So this one had to flip as well. So when it's all said and done, I can find it in my work. You add them up. And it gets 2 points. 1 point is earned for recognizing that you probably either flip or take half. That's the way they probably would word it. And then 1 point is earned for the correct answer. So obviously, to get it right, you'd realize that you'd have to flip one and take half for both. So that's what they kind of assume. Like if you didn't get the right answer, you probably didn't do all of it right, but they're going to give you credit for something. I don't have the final answer, but I'm guaranteeing you could probably figure that out. All right. This one actually doesn't have a lot of work in it, so we'll talk about it. The electrochem. It's good to see. So here we go. Electrochemistry, always good to go over. These questions kind of come in and out from time to time. I need you to understand that in electrochem sometimes there's really simple answers. There are things that really, like just electron configurations. They joked about this once. Years ago, there was this electrochem problem for A and B, and then the next like 5 letters were all about this electronic, electron configuration and a valence electron.
You're struggling. Yeah, that was good.
I said the word twice.
I think it was like 5.
Okay, you want to do the next one?
I got a clicker.
Right? I mean, I'm just thinking. I mean, you want to see?
I'm sure I'll be
Okay.
smarter for it.
All right. Well, anyway, it was a really good story. I guess I need to talk about it. Write the complete electron configuration for Zn2+. So what does that mean? I need to know how many electrons I'm dealing with. So zinc has 30 protons. So how many electrons do I have? I have 28. So what you have to do is act like it's 28. The reason why it's a +2, so it's a difference of +2. It says the complete. If you want to get lazy and write just the valence electrons or the noble gas configuration, you're going to be in a lot of trouble. So you have to get through all of it. So you do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Did I struggle with that? So that will equal 28. Which species, Zn or Zn2+, has the greater ionization energy? Justify your answer. So you will have to get specific on what ionization energy is all about. Okay.
It's Cn2 plus with the electron configuration change. It's plus.
Right, it would be 3d10. It would be 3d10. But I'm going to 28. Yes, it would change. Ionization energy is about the energy required, this is not the answer, to remove an electron. Okay? It's the most important one besides like atomic radius, but like this comes up a lot. How difficult or how easy it is to remove. It's not about wanting. They don't want to. It's more difficult to remove or it's easier to remove. Well, why? It's being held tighter or held looser. That's it. Oh, they want to read. No, it's not about wants. So which one would be have a greater ionization energy? Well, there's a couple things here, but to me, it's more about the difficulty. So Zn, what you're doing is trying to remove the last electron on 30 electrons. With Zn2 plus, you're removing the last electron of 28 electrons. So think about pull. You have 30 protons for both. So which one's going to be more difficult to remove? The Zn or the Zn2 plus? Those are the two options. Those are the two options. The electron cloud, there's a couple options. Electron cloud is smaller. Each electron is held tighter. Right? Why? Because they're outnumbered. Think about it. Each electron is being pulled just a little bit stronger because the protons aren't as diluted. Right? You can think of it a lot of ways. I want to read what it says. It takes more energy to remove a No, that's not the one I want to read. Zn2 plus has a greater ionization energy. The electron being removed from the Zn2 plus experiences a larger nuclear charge than the electron being removed from the Zn because Zn2 plus has two fewer electrons. Nuclear charge just means they have the same nuclear charge, but each electron's feeling a little more of it because there's less of them. C, identify the species that's being oxidized in the reaction. Right here. To be oxidized, you go up in charge. Reduce means you reduce your charge. So which one, Al or Zn, is being oxidized? It doesn't even say explain. Al, it goes from 0 to 3 plus, right? That's it. So be Al. I'll say that again. Oxidation involves loss. Be careful. Loss of electrons. You lost 3 electrons. Okay. All right. Finishing up with this one. D. Wait, so the diagram shows a galvanic cell based on the reaction. Assume that the temperature is 25. D. The diagram includes a salt bridge that is filled with a saturated solution of KNO3. Describe what happens in the salt bridge as the cell operates. Okay, so you have to explain that. Well, you could draw it right here, but I'll just do it this way. We don't have time to do a lot of explanations here, but to me, this is the key thing you need, and I would draw on your sheet. You need to know where it's going, and I don't know if you can tell, but Al lost electrons. I'll say that again. Al lost electrons. So electrons are going, I don't know if we have to label this later, but I'm doing it now anyway. It's going to help you in the long run. Electrons are traveling this way. If electrons are traveling this way, check it out. Al is going to Al3+. So it's going that way. Let me do it in color. It's going that way. Like, it's going out of solution. Electrons are hitting this, and it's getting too negative, so the positive ions are going in there. Well, why am I drawing that? It's important to have an idea what's happening. I'm gaining positives here. The charge of the solution is gaining more and more positive, so which ion needs to counteract that? The NO3 needs to travel in this direction to help offset the increase in cations. I'm losing positives here because it's coming out of solution and plating onto the metal. So the positive ion in the salt bridge needs to travel to the right to offset the lack of positive ions. You cannot get overloaded or lose charge, or your cell will die. Okay? So that's, you might have just been able to do an arrow. but it says described, so you have to talk about it. So again, it's just realize if you're gaining or losing, the cell bridge is there to counteract, either to offset it or to replace the missing amounts. E, determine the value of the standard cell voltage. Okay, so I don't know if you were given values. Okay, assume that you had these somewhere. These would, when this test problem came out, I think you had to have these. So I will help you just understand where this would have came from. It's important to write this on the side. These numbers would be given to you. Quick talk about this. These would be given. This has to be given. And I don't think it's on there anymore. Like, this has to be given to you. It'd probably be in a little table. So, as we're finishing writing this one, big deal. You can't have electrons on the same side. Which one of these does not correspond to the equation above? Like, one of these is in the right order, the other one is not. Which one does not correlate? The aluminum one or the zinc one? Aluminum. These are always called reduction potentials. We just said that the Al was being oxidized. The one that's oxidized has to flip. So this one has to flip. What's the other issue? It would be, well, initially it's negative. It's also you need the same number of electrons. We'll talk about that later. So that's why this had to be multiplied by 2 and this by 3. But what's weird, it doesn't affect this. So let's say you didn't have this problem and you just had this. And I said, write the equation. I know to flip this one because you have to make a positive voltage for a battery to occur. So you have to flip the one that will create the addition of a positive voltage. If I flip this one, I'm still going to have a negative voltage. When we flip it, we flip the sign. So without even looking at the equation, you should have already known that this one should have been flipped because they wouldn't have made a positive voltage otherwise. So when I add those up, I'm going to ultimately have plus 166 minus 0.176. And I know that seems odd, but the voltages are not affected by values, by altering the magnitude. Okay? I guarantee that's worth 2 points. What number? Are we on F? We may or may not get to the equations, and that's okay. I knew that coming in that we might not. Can't read. Indicate whether the value of the standard free energy change for the cell reaction is positive, negative, or 0. Justify your answer. Doesn't say anything. Let me tell you. Let me say you wouldn't even need to do an equation. How do I know the answer to this? And you could do one, but you don't have to. What is change in G is what? Anybody? Ken?
Is that like whether or not it's spontaneous?
Yeah.
So what, just spontaneous if it's a battery?
Okay, so then what sign would that have?
Negative.
Perfect. It is a negative, so that's spontaneous. And the reason why I know is that the battery is creating voltage. Or it's running, or let me see if I can read it in any other ways. I mean, it must be negative because the battery is functioning. It's a naturally flowing battery. It's a natural, it's producing natural current and voltage. So it's spontaneously occurring. How do I know, by the way? If it's not, this is not a voltmeter. That's a battery. If there's a voltmeter, it's a natural occurring battery. It's a galvanic cell, which has also been stated, I believe, right there. Okay. And G. If the concentration of AlNO3 in the AlAl3 plus half cell is lowered from 1.0 to 0.01 at 25 degrees, does the cell voltage increase, decrease, or remain the same? So, this will probably be our last question for the day. If I lower this, so I lower, just want to make sure I'm reading this right. I lower the cell. Now, there's a Nernst equation. It's not a big deal, but you could kind of see the Nernst equation. And what it always does is it causes, you put the ions above each other, the solutions, and it's always the direction it's going. So this is kind of like the products, this is the reactants. I don't expect you to have that memorized. It's on your yellow sheet. I know I'm down here. But I think of it this way. This one, if I decrease this one, I mean, I'm needing amounts to fulfill this. And if I run out, it can't work. This one is simply getting more from the metal. So this one's not nearly as contingent, but what it does is it creates a greater potential between the two, which causes this to even have more Al go into the solution. And more Al could go in there faster. So because of this, like the Q would increase and affect the voltage. I know that's a little, you're not going to have a great understanding of that until we get into the equations again. But just by looking at that for now, what I'm just saying is that that's going to drive this reaction even go harder. So it'll actually increase, and they have a longer explanation than this, but it will increase the potential of the cell. Okay? So that will increase. We will touch base later on those equations, but I'm not nearly as worried because that is still old format. The other things are much more important for now. So thanks for coming. We'll continue to talk. AP format 1 and 2, that is all that is technically due tomorrow out of the packet. Please be doing the first and second aqueous chapters 14 through 16, though. I'm stamping those. Just the first two. Make sure you're doing the right ones. We're going to go over those as well. Redox is due later in the week.